Welcome back. This is the first part of the video on 2.3 polynomial functions of higher degree with modeling. I've got this note guide here for you, and if you're following along, a lot of these things we've kind of talked about already, and we're going to take that basic understanding that we have and we're going to expound upon it. Polynomial function. As we've discussed in the past, a polynomial kind of takes this form, and this is going to be that form with a lot of coefficients and subscripts, and we've learned to identify polynomial functions, but this is the nuts and bolts of what's actually going on there. And so if I'm looking at a polynomial, I've got a sub n times x to the n, and this is going to be, the leading coefficient, and this is going to be the highest degree term. We're talking about standard form here. And as we go down the line here, we're ticking down the term number. So if this is the fifth term, this would be the fourth term, assuming that it's got all of them in it, all of the given coefficients or terms. And so as we march down the line here, we eventually get to a point where we're adding a sub 2 x squared plus a sub 1 x to the first plus a sub 0, and a sub n is not equal to 0. This polynomial function has these coefficients and exponents and coefficients and exponents, and they're in order of from highest degree to lowest degree. So as we talk about these, if we had, for example, f of x is equal to x cubed plus 5, this would be called a cubic function, because we're identifying it by its highest degree term. So this is an x cubed. If we had f of x was equal to 3x to the fourth minus 4, this would be a quartic function. And the reason why we're identifying them is because we're going to learn in this section that it's very important what the lead term is, what the highest degree term is, because that's going to dictate what our behavior on our graph looks like. So let's do something that we've kind of looked at before. We're going to describe the changes of f of x is equal to 4 times x plus 1 cubed. Well, our basic is f of x equals x cubed, and so all of our changes are going to be based upon that. So what we see is we've got this 4 out front, so it's a vertical stretch by 4. We've also got this plus 1 in here, which means it's going left 1. And so if I were to graph my x cubed function here, and it went through 1, 1, and it went through negative 1, negative 1, because that's my basic structure of my cube. What would happen is my new function, which would be this one, I'll circle it in green, the vertical stretch of my coordinate here would go up to 1, 4 and down to negative 1, negative 4. But then, so this would be over the first transformation, and I guess I should specify that. That's with this one. And then if I graph in red, my final one, it's going to be left 1, so this here, and then here. So my final curve is going to go up something like this. Well, what do we notice? Now, instead of going through the origin, what's my y-intercept? My y-intercept is equal to, well, if it was at 1, 4, then it would go over 1, so it would go to 0, 4. Well, how could I figure that out? How could I know what my new y-intercept would be? If I put in, really, f of 0, because at my y-intercept, my x is 0, it would be 4 times 0 plus 1 cubed, which would be 4. So my y-intercept, in fact, is 0, 4. That's a verification that I've moved it correctly based on my new y-intercept. In the second example here, we've got a similar evaluation of a function that we've already kind of looked at. So our basic is f of x equals x to the fourth. And we know that that goes through 1, 1. We know that it goes through negative 1, 1. And so it's a little bit wider, kind of goes like this. Right? What are my changes? I've got this negative out front, so it's flip over x. It is right 2. And it is up 5. So let's see if we can't work a little bit here. I'm going to flip over x here. So I'm going to take it down, and then we're going to go this way. So this would be 1, negative 1. And if it seems like this is familiar, we've done some of this before, but we're looking at these families of functions here. And we're looking at polynomials, and the ability to look at a function and say, well, these are what the changes are, hugely crucial. Okay, right 2. So I'm going to take this from 0, 0 to here. This point's going to go to 3, negative 1. And I hope that this isn't too close for you. The color, I mean. I hope the color's not too close. It's pretty close, that color, that blue and that green. And so then I'm going to go up 5, and my red is going to be my final. So I'm going to go up 1, 2, 3, 4, 5. So my final curve is going to look like this. And it's f of x is equal to negative x minus 2 to the fourth plus 5. Okay? And so I'm able to use these changes in the function to graph the changes, moving it incrementally. And as we've seen with power functions, as we've seen with transformations in the coordinate plane, these basic skills are crucial to us understanding how do these families of functions relate. Because what we're going to do is now we're going to take two monomials, so for example an x cubed and an x, and we're going to combine them into one function, and we're going to look at what that does to our graph. So in this example, we want to graph the combinations of functions, describe the extrema and the zeros, explain how it is related to the monomials from which it was created. So let's graph. And actually, I'm just going to pull up a graph here that I've already got for you going. And as you can see, try to do kind of a split screen here. X cubed plus x. Well, what I did was I graphed those two separately so we could see. So obviously this green is the x, y equals x, and this blue is the f of x is x cubed. When I combine them, so I'm going to add them together. This would be like, f plus g of x, something like that. Check out what happens. What does this red one look like? That's the question that we're answering. It's asking us to describe. Well, it kind of looks like the blue one. It looks more like the blue one than the green one for sure. When I zoom in, take a look at what happens. Which one does it look more like? Well, and the answer becomes a little bit trickier, but essentially, here's what's going on. It looks like the red one, because if I zoom out, check it out, or it looks like the blue one. As I zoom out, which one does it honestly look more like? It looks more like the blue one. But how does the x part factor in? As I get very, very close to the origin, it looks most like that x one. So how do we describe this? We're going to say something like this. F of x looks like x cubed when zoomed out. However, around the origin, it looks like y equals x. So let's do a little bit of graphing. Here's what we're going to do. We're going to graph y equals x cubed. We're also going to graph y equals x. So I'm going to do it in pink on mine. Okay? And our curve is going to look like something like this. Let me check my, so let me zoom out a little bit. My red is skinnier than my x cubed, so it's going to go this way. But it's going to look, and it's going to follow y equals x around the origin. Okay? So the green one is f of x equals x cubed plus x. Okay? So it looks like x around the origin, just kind of following it, but as you zoom out, it looks more like that x cubed. See if you can do the second one. So see if you can plot this one, and I'll pull it up for you here so you have an idea if you're correct. So here is my purple one is now my x cubed minus x. And so as you think about it, what does it look most like? Okay. What does it do around the origin? And what am I actually comparing it to? And I'm going to give you a hint here. If you look at this part, are we supposed to be comparing it to y equals x? It's really more like y equals negative x. And as you zoom in, think about what you notice. So describe that one. Pause this video, describe it, and right after the pause, I'm going to work with you on what the actual answer is. So go ahead and pause now and try it. All right, we're back. So if you graphed these, what you ended up with was y equals negative x, that's this part here. Okay, and we also graphed that against y equals x cubed, so this here kind of. And our graph, as you recall, was a little bit bumpier, but it looks like this negative x around the origin, but as we zoom out again, check out what it looks most like. Boom, look at that. It doesn't actually follow negative x really at all, except around that origin area. And so as I zoom back in here, let's graph. Use a green color here. It's actually going to be something like pretty close. Okay, so f of x is like x cubed when zoomed out. X cubed is the highest degree term, remember that. But around the origin, it looks like y equals negative x, so the other part of the function. Okay? And so as we move on here, we're going to discuss end behavior. We're going to discuss what it looks like when you zoom out. And we're going to have this little theorem here that talks about the local extrema and the zeros. Part of the instructions up here were to look at the extrema and the zeros, describe them. Well, what about our extrema here? Our extrema and our zeros were shared on this one. Our zeros were shared on this one, except when we got into our f of x, right? Because I've got an extra zero here, an extra zero here, and they look more like the highest degree term. And so being able to find these, we've done that already. We did, calculate the max and calculate the min. But what we're going to be concerned with going forward is how many zeros are there? What do they look like? What's the function of those zeros? And so we've got a theorem here that says local extrema and zeros theorem. This theorem says this: a polynomial has, and this is of degree n. So x to the third has at most n minus 1 local extrema and at most n zeros. So let me emphasize this. At most n minus 1 local extrema, so local maxes and local mins, and at most n zeros. Okay, so as we look into these graphs, as we're moving forward through these graphing exercises, we're trying to figure out, how many zeros do we have? Can we find them? What's their multiplicity? That may be a new word for you. And so as we're looking at these things, we're trying to figure out, where are we at in terms of our zeros? What are they? How do I find them? Okay? And so as we move forward through this, that's the first part of this lesson. We'll do this exploration in class together, and then we'll spend some time talking about leading coefficient and the highest degree term, finding big windows by zooming out, and finding zeros and finding their multiplicity. Okay, so that's the first part of this lesson. Thanks for watching. Make sure you took notes, and if you have any questions, please write them in the margin and let me know. Okay, thanks for watching, and we'll see you next time.